So let us start.
Yes, sir.
Actually, from I don't probably we have ended our last lecture at this point. Actually, what have we done so far is classifications of our signal,
Yes, sir.
and we started our classification with some basic properties of signal, and they're expressed mathematically. So in addition to their classification, we need to operate on signal. Actually, what do you mean by operations of signal? Actually, whenever we say that we have a system just designed to process a signal, that processing is actually mathematically some form of operations, okay?
Yes, sir.
For example, if you want to amplify the signal, you need to multiply or you need to reduce the amplitude of your signal. If you want to reduce the amplitude, this becomes a simple. It's just if you want to explain the thing very simply, that it becomes a multiplication operation. Okay, depending on the factor of multiplication, your signal can be amplified or the amplitude can be reduced, isn't it?
Yes, sir.
Similarly, your signal can be subtracted, your signal can be added, your signal can be divided, or your signal can be operated in terms of some logical operations, okay, or and XOR or something like this, okay, that you have learned in your digital electronics, okay, because these operations and or XOR complement all are operations at the basis of computer arithmetic. At the same time, we can have some logic there. That logic will transfer, for example, the signal condition from one state to another. All this belongs to the operations of our signal.
Yes,
So
sir.
if we want to categorize this operation into two broad categories, then what will happen? We know that your signal is expressed as a function of one or more independent variables. Okay.
Yes, sir.
If this is the case, then what will happen? Your signal itself is dependent variable and it contains an independent variable. It can be one or more. But in our case, we are considering a one-dimensional signal, so our variable principally will be time or space. We are considering time first, that xt is our signal. If xt is our signal, xt is itself an independent variable. So the operation of xt has two perspectives. One, either its amplitude can be scaled. Amplitude scaling means what? A multiplication type operation, okay?
Yes, sir.
Or it can be integrated, or it can be differentiated, something like this.
Yes, sir.
But we have another operation is called operation on independent variable. Operation of independent variable is very important and a bit complicated than operation in its dependent variable. The reason is that whenever we are operating on independent variable, what will happen? It will change the time step or time behavior of your signal if your signal is time dependent, or if your signal is space dependent, it will change the space dependency of your signal. Okay, consider first with an example. I don't know, I have discussed the thing earlier with a sinusoidal signal. Okay, let us build our concept by using a simple sinusoidal signal, then we will come to this slide again, okay?
Yes,
So
sir.
you can hear me clearly.
Yes, sir.
Yes, sir.
Okay. Then this is your whiteboard. Let us examine this property by using our known example that you are seeing from the very earlier level.
Yes,
Consider that we have a signal xt. That signal is equal to, say, at amplitude equal to a, it is sine omega t, something like this, okay?
yes, sir.
If we plot this signal, it is it is an everlasting signal. That means it time starts from minus infinity, goes to infinity, okay?
Yes, sir.
But we are just drawing only the positive part of your signal. Consider 1 second only, okay?
Yes, sir.
So this is your time period, you know this thing. From this time period, you can calculate your frequency. Your frequency is equal to 1 over t, okay?
Yes, sir.
And as it is a sinusoidal wave, we don't have any other frequencies. But if it is non-sinusoidal periodic wave, it will have many frequencies that you need to extract by using Fourier law,
Yes,
okay?
sir.
Fourier mathematics, okay?
Yes, sir.
Now consider that in this signal itself is an dependent variable. It depends on time t. So if you want to scale the signal scaling means you are multiplying the signal by a factor k. For example, say we are multiplying this signal xt by k. We have a device, that device is producing a signal yt, that yt is equal to k into xt. If we multiply this signal k, then what change will be there in the signal? Your
Sir.
amplitude A will be transferred into amplitude k multiplied by A, isn't it?
Yes, sir.
That means this signal will be simply k. This is also multiplied by k. This is your yt then, okay?
Yes, sir. There will
Is it
be vertical stretch.
okay? And this is called scaling, amplitude scaling up, or
Yes, sir.
this is your amplitude scaling operation. Scaling means what? Making it large or small, something like this. It is simply a multiplication type operation. Even you can differentiate it, you can integrate it. No matter whether you integrate it or differentiate it, would it change the time profile of your signal?
No, sir.
For example, if we differentiate your signal xt by dt, then it will be equal to A into cosine omega t.
Yes, sir.
Only your phase shift will occur, but no frequency will change. Similarly, if you integrate it, it will be equal to minus cosine, and again it will not change the frequency. So all these operation will change. These are the mathematical operation. This will not just change, but it will shift your signal or make some changes in your signal in terms of time nature, but time scale will remain same. Time axis will not be scaled, okay?
Yes, sir.
For example, say if we have a signal xt is equal to say t, and that t exists from time t equal to 0 to t2, for example, say t, then your signal will look like this, something like this, okay? This is your signal, this is your
Yes,
xt. Now if we integrate it, it will not, for example, change the t, okay? Time scale will remain, this scale time, that will remain same. Now we try to understand from this known example, then I will be going to this type of discontinuous signal later, okay? Because it needs further discussion.
yes, sir.
So consider now that we are operating on the independent variable t, okay? We are replacing our t by say 2t. Then your signal yt would be equal to A into sine 2 omega t. Okay, what will happen then?
Sir, frequency change.
Frequency changes, but in a what amount?
Sir, it will be.
You see that your frequency, angular frequency omega is transferred into 2 into omega.
Yes,
That
sir.
means your frequency f will be equal to twice f. Your time period now t becomes your half, okay?
Yes,
Original t divided by 2. So in a single time period, you see 2 cycles of your signal will be completed, isn't it?
yes, sir.
So what does it mean? That initially your period was something like this. When we multiplied it by 2, your signal, one cycle of your signal is coming in this region, and that is equal to t divided by 2, isn't it?
Yes, sir.
That what does it mean then? It means that your signal cycle is compressed,
Yes,
isn't
sir.
it?
Horizontal compression, sir.
Yeah.
Horizontally compressed.
Horizontally means in time domain, independent variable, it is being compressed, okay?
Yes,
Thus, your signal is compressed twice in time. Similarly, if we make our multiplication factor 1 by say half, then it will increase the frequency 2, okay?
yes, sir.
Similarly, your signal will be expanded in the time domain. So this situation, whenever we operate our signal in independent variable, then what will happen? Your signal will either be compressed in time domain or will be expanded in time domain. Along with your expansion and contraction, we may have, for example, an operation of our signal. For example, say when we change, differentiate this signal, something like this, can we write this signal in this way that cos omega, this can be A into sine omega t plus 90 degrees, something like this. Can we write this?
Yes, sir.
That 90 degree can again be transferred into time. Can we do that? Because we know that omega t0 become 90 degree or pi by 2. Okay.
Yes, sir.
Then your t0 would be equal to what? Pi divided by 2 omega, isn't it?
Yes,
Is
sir.
equal to pi divided by 2 into what? Twice pi divided by t. So I am putting t over. So this is simply equal to t divided by 4, isn't it?
Yes, sir.
So you can write this signal in this way, that it will be equal to A sine omega, place your omega common. This is equal to t plus t divided by 4, isn't it?
Yes, sir.
So this means that your signal, if you plot this signal, you will see that your signal will be going in which ways? Your signal, your cosine signal will be something like this, isn't it?
Yes, sir.
So in compared with your blue curve, with red curve, your red curve is advancing in this direction. For example, by an amount is equal to what? Minus t divided by
Yes,
4,
90 degree.
or equal to 90 degree or pi by 2. That means it is a time shifting operation, okay?
Yes, sir.
So we have two operations in general in independent variable, okay? One is called is time scaling operation, another is time shifting operation, okay? That we will be again going to the slide. Is that clear?
Yes, sir.
Yes, sir.
Okay, so we have this example there. Now this signal is not sinusoidal, but it is a triangular or something like this. But still the same logic will be applicable, okay?
Yes,
Now consider that this is your original signal. Figure A is your original signal, okay?
sir. Yes, sir.
Now what I have told you earlier, that your signal can be given in figurative form or it can be given in mathematical form, okay? That you can draw your signal by using mathematical equations, or you can derive your signal from a figure, okay? No problem.
Yes, sir.
Now say this signal is operated in this way to find the signal yt equal to x into at. A is a general multiplier or a scaling factor in time. It can be greater than 1, it can be positive, it can be negative, or minus, it can be 1, okay? Now you see that if we have this signal, now just a numerical example is set first, then generalized will be there. Like our previous case, you see, when we replace our t by twice t, the value of A become 2, and in essence, what is happening in your signal? It is compressed in the time domain, isn't it?
Yes, sir.
Compressed by what factor? By a factor of 2. That means
Yes, sir.
you want the signal that starts and 1 will be at half, and the minus 1 will be equal to minus half. But the position of the signal with respect to the coordinate time t equal to 0 will be remaining same, okay?
Yes, sir.
Yes, sir.
If we go in the reverse way, that if we make our signal the factor half, it becomes less than 1, and your signal will be expanded in time twice, okay?
Yes, sir.
So your 1 will go to minus 1 will go to 2, and 2 will go to minus 2, minus 1 will go to minus 2.
-2. Yes,
You
sir.
can easily verify this thing. For example, for this case, I am showing this thing in order to verify, okay? We have some other shortcut techniques I will be discussing later. So you just, by using some intuitive approach, you can easily verify that this expansion is correct.
Yes, sir.
Consider that we need to consider 2 points. We need to calculate our signal, say at y equal to 0. If we set y equal to 0, that will be equal to x0, isn't it? That means the output y of this operation at time t equal to 0 would be equal to the value of your signal at equal to 0. The value of our signal is x equal to 0 is this, and this is there, okay?
Yes, sir.
So it is satisfied. Now we want to calculate the value, for example, of t equal to say t equal to say 3. Consider, okay? Say we want to calculate the value of your signal at t equal to, that will be equal to what? X t divided by 2t, isn't it? It will be equal, because it is half t, so t equal to 3, it is x 1.5, isn't it?
Yes, sir.
Yes, sir.
Is there any value in this figure, original figure, at this x? X 1.5, is there any value at t 1.5?
No,
No,
sir.
sir.
No, so no zero. Then value starts at what? Value starts at, if you want to
Zero.
calculate the value, then it starts at, for example, -2. That y minus 2 would be equal to x minus 1. Similarly, your y plus 2 would be equal to x1. Okay, if we go beyond this time in either direction, then what will happen? No signal is available. So you can easily calculate that in y, your y minus 1 will be appearing at y minus 2, and y plus 2 is appearing at x plus 1 is appearing at y plus 2, isn't it?
Yes, sir.
Yes, sir.
So your signal is getting expanded. So this can be generalized, that if you multiply or scale the time of your signal by using this operation, then depending on the magnitude of A, either your signal can be expanded or signal can be
Compressed.
compressed.
Yes, sir.
Now you have to understand by your own. I am just leaving this thing as a self-exploration. Okay, this will be important for your test. That when a signal is expanded or your signal is contracted or compressed, what effect will be there on the energy? Okay, so this is your not assignment, for self-exploration. Okay, it will be there in your exam. That means
Yes, sir.
what is the effect of time scaling operation on the
Energy.
energy of a signal. Okay, okay, try to explore it.
Yes, sir.
So because this is annotated something, if you keep the note, I can erase it, because otherwise. Okay, let's go to the next slide. Okay, keeping this thing there, and we'll erase it. Oh, okay, fine. I am now illustrating the same operation for you, discrete time signal, because we have two classes of signal. One is discrete time, another is
Continuous.
continuous time. But discrete time understanding is continuous time understanding on operation is a bit easier. But understanding this operation for discrete time signal a bit tricky. Then you have to understand the trick. Okay. Consider then we have an xn. Okay, that xn is a sequence of number. For illustration, it has been considered that we have a sequence of numbers extending from -6 to +6. Okay, consider that in discrete time signal, as it is being represented by xn. So your value of n must be integer. No non-integer value will be applicable. You consider the thing?
Yes.
Okay,
Yes.
you understand the thing. No non-integer value can be used as a sample point. All
Yes,
will
sir.
be integer.
Integer. Yes, sir.
Yes. Now we have a signal something like this. Oh, sorry. Okay, we have a signal something like this. Then if we want to operate this signal on the independent variable, here in this case, your signal is xn is equal to xn. Okay, operating on amplitude means multiplying this signal by a factor a. That will simply increase or decrease the length of this stem. Okay, it will not change the value of n. Another operation, this is operation on dependent variable. If we want to operate it in independent variable, then this is what that operation. Okay, that means we are making a signal yn. Yn is equal to x into kn. That means u samples are multiplied by kn. Your n must be integer. K should also be integer. Okay, In your continuous time case, when you operated with AT, your A can have a real value, no integer, or it can be integer, non-integer, whatever it may be, okay? But one restrictions there really would be in discrete time signal, that as it is discrete, your time is sample replaced by sample points n. So whatever operation we will be doing on independent variable, we are operating n. So n is an integer. That integer operation can be what we call some integer type, but it can be divided by or it can be multiplied, okay, something like this. But it will be resultantly, whatever you will understand that whenever we are obtaining a signal yn equal to kxn, your yn should be integer, and those value of y will be appearing at the output at integer values of n, okay. Now consider that we are illustrating this operation by using this example. Our sample is extending from n equal to -6 to 6. Now we are having a system that is making our signal yn is equal to x to n. That means we are multiplying our n, the sample by 2. Now let us map few signal points in our new signal, okay? Fine. If we want to calculate, for example, y0 would be equal to what? Y0 would be equal to x0 for n equal to 0, isn't it?
Yes, sir.
Yes, sir.
So this x0 is coming there. Is it okay?
Yes, sir.
Yes, sir.
Yes, sir.
Now we need, let us calculate y1. Y1 would be equal to x2, isn't it?
Yes, sir.
So we have our x2. X2 is coming there. Similarly, if we want to calculate y minus 1, that y minus 1 is equal to x.
Of -2.
Sorry, x. Y
Yes.
minus 1 is equal to x minus 2,
Yes, sir.
isn't it?
Yes, sir.
So we have our x minus 2, that x minus 2 is coming at y minus 1. You see that in this way, if you go from -3 to 3, you see that in yn only n equal to -3 in the lowest case, n equal to +3 in the highest case are possible, isn't it?
Yes, sir.
If we, for example, want to calculate y minus 4, it will be equal to x minus 8. We do not have any signal in this region. Similarly, if you want to calculate, for example, y4 would be equal to x8. We do not have any x8, okay? Is that clear?
Yes, sir.
Yes, sir.
So can you tell me that effectively what is happening there?
Half of the data points are
Half of the data points are disappearing. Yes, that's
Yes,
good.
sir.
That means half of the data points are sample are disappearing, and that is actually compressing your time axis by twice. That is equivalently equal to, we use a term in our digital technique, we call it downsampling, okay? We call it
downsampling.
downsampling, because downsample means you are reducing the number of sample, okay? If we multiply it by 2, your sample will be reduced to half, okay? Now the question is that in the case of continuous time signal, if we compress or expand our signal, we can bring our signal exactly into the original form theoretically by reversing the operation. But if we want to reverse the operation to go back into xn, what you need to do?
Sir, multiply with the
That means you have your x twice n will be there. Then if you want to find our xn, then xn should be equal to y into n by 2, isn't it?
Yes, sir.
But if we want to do this, you will see that you will be obtaining this signal for n equal to 0, your 0 signal will be there, no problem.
Yes, sir.
For n equal to 1, you will have a signal there half. Is there
Yes,
any
sir.
half integer is not possible?
No, sir.
Isn't
Yes,
it?
sir. Yes, sir.
So then if you want to plot it in this signal in the reverse way, you will have this signal there, but at n equal to no signal, okay? Similarly, this signal will be there, no signal. That means a 0 will be inserted between these two, and it will increase the number of sample from -6 to 6. But this is not the exact yn, is it exact?
No, sir.
In terms of numbers of sample, it can be same. but the signal is not exactly. For this reason is digital technique. If you want to upsample it, this is called upsampling, okay? Upsampling.
Sir, the previous one was downsampling, na, sir?
The previous one was downsampling, okay?
Yes, sir. Yes, sir.
Are not the thing very interesting?
Yes, sir.
Very interesting something. So engage, okay? Only you 2 or 3 are responding. Others are sleeping, I hope. I think.
No, sir.
Do not
No,
sleep,
sir.
okay? Because
No,
you engage. These things will be the only thing that you need at this time.
Yes, sir.
Okay,
Yes, sir.
you don't have any other important thing than you're learning now. So, your upsampling, downsampling is the eliminate your sample by a factor depending on how many times you need to downsample it. Upsampling is the reverse operation of downsampling, but the thing is that your signal cannot be exactly recovered. For this reason, we need some statistical and mathematical technique to estimate the sample where its value are 0, okay? In your numerical method, you understand, and that is what the point where you need your numerical technique, okay? In your numerical technique, you know, a mathematical technique we call interpolation. Have you heard about it?
Yes, sir.
Yes, sir.
Yes, sir.
Interpolation.
Yes,
Yes, sir.
sir.
One is called interpolation, another is called extrapolation, okay?
Yes, sir.
Interpolation means if 2 or 3 data values are given to you, by examining the nature of these 2 data values, you can estimate the intermediate unknown values, okay?
Yes, sir.
This is called interpolation. And interpolation should be made in such a way so that error will be minimum. Extrapolation is that if you want to do the same thing outside the range of your signal, then this is called extrapolation.
Extrapolation. Yes, sir.
Yeah, so we have definite algorithms. You have learned Lagrange's interpolation, binomial interpolation, even by simple trapezoidal rule, you can interpolate or extrapolate, okay? That doesn't need that much rigor in the mathematics. For example, if this is something, averaging technique can also be used there. For example, say if we make a running average of this signal, that means we are adding these 2 samples and dividing by 2 and replace the 0 by this thing, okay? Then what will happen? Your signal will be something like this, isn't it?
Yes, sir.
This point will be, 0 will be replaced by the average value of 0 and this signal. This can one of the interpolation technique. So there exist many other interpolation technique. You have your higher course of digital signal processing that will, although it is one of the what you call mandatory course, I would say nowadays, because without the idea of digital signal processing, you cannot process your signal nowadays because we need computer to do that, okay? So at that case, it will be cleared, I think. So all these things are described there. You try to explore the next figures or some text are there in your book by your own. I hope you'll understand it. So this is how your signal will be operated in your independent variable. This is called a scaling operation, okay? In your independent variable. Now we have another.
Sir, a question, sir.
Yeah.
Sir, by interpolation, we can estimate some values, intermediate values, like the value between 0 and 1. But the main signal xn, there is no value between 0 and 1. So if we do interpolation, so it will not be the same signal. So won't it affect the...
What? In which case? In what case? In continuous time case?
When we are doing interpolation.
Interpolation is always an approximation. It cannot be exact, okay? Interpolation is always an approximation, okay? You have to interpolate in such a way that your error would be minimum. In your continuous time signal, if you want to expand and contract, you do not need your interpolation because your signal will be there always continuous. But in the case of discrete time signal, in this case, interpolation will be needed, okay? But in many other purposes, we need interpolation. Okay. For example, if you want to draw a curve, do you have any idea of drawing curve by using your Excel or any other computer program?
Yes, sir. Yes, sir.
But then how Excel will draw a, for example, you are giving 2 data points only, or 3 or 4 data points only. Say you have a data point there, you have a data point there, you have a data point there. Your Excel can draw a figure something like this. Or your Excel can draw a figure something like this, isn't it? How
Yes,
these
sir.
continuous curves are drawn. This is your interpolation. Okay, you must know it. Spline type interpolation. Have you heard about it? Bezier curve, spline, all things are
Yes, sir.
related
Yes,
to
sir.
interpolation. Okay.
Yes, sir.
So these things will be there. They will just take these two values and feed these three values to a curve. This interpolation technique can also be segmentally used in curve fitting. Have you heard about curve fitting? Or
Yes, sir.
least square approximation in your numerical technique?
Yes, sir.
Yes,
Or
sir.
regression analysis?
Yes, sir.
Yes, sir.
So all these belong to the approximation technique. Okay, interpolation is one of them. Okay, interpolation, it cannot be exact. It will be just follow the trend of your signal. Okay, that's why in your Excel we call it, if you assign your Excel to draw a curve, it called trend curve. Okay, it will draw a trend curve in which mathematical trend it is following. Okay, so we can discuss much about it with later. Okay, but let us complete our discussion at this point first. Now we have our other operations there. Okay, I will try to give you an example how interpolation works later, okay? By using a simple class 5-6 rule, trapezoid. Is it okay? Can you hear me now?
Yes, sir.
Okay. Is your recording going on?
Yes, sir.
Yes, sir.
So, because I will not record the same thing for other sections, because this thing will be repeated. And today I have to take 3 classes. Okay. Now we have another operation that we have already illustrated for the case of even and odd signal, and if a signal is neither odd and nor even. This is again reiterated here, try to understand it. That operation is called reflection or reversal in time domain, or flipping your signal with respect to the vertical axis. Okay, if we have a signal, for example xt, and you know this signal I have already illustrated in my last class. So if we have this signal, then if we want to flip the signal with respect to your x-axis, y-axis, that means your vertical axis, then what you can do, you can consider that we are placing a mirror on this axis and try to examine the image of the latter part of your signal on the mirror. Then what will happen? You will see that in the mirror, this part of your signal will appear as an image, and you just flat the mirror to align with this plane. Then you will see that this part of your signal will be coming there, and that part will be coming there. Okay, this is called reflection or time reversal operation. Okay, another operation we need, that operation we call time shifting operation. Time shifting operation is needed in many of our signal analysis. Either your signal can be shifted in time where you receive the signal, then we have to bring back your signal in time, then this shipment will be needed. Okay, consider that we have a radar. Okay, have you heard about radar?
Yes, sir.
Okay, do you know how does it operate? For example, it detects an object in a distant location by sending a signal to the radar, okay, to the object.
Objects. Yes.
Then that object will reflect that signal. Okay, if that object is reflecting that signal, again it is coming to the sensor of your radar, it will sense it. So there exist many techniques, for example, to detect the signal. One of the techniques is that if you want to examine the nature of the signal, for example, you are sending the signal at time t equal to say 0, and you are receiving a reflected version of the signal at a later time, isn't it?
Yes, sir.
Then what will happen? A time translation will be there.
Yes, sir.
So if you want to, for example, say we have a signal, that signal you send a pulse, then you are receiving a signal, for example, something like this. It is not exactly equal to pulse. But if to correlate these two signal, correlation means what? Just to measure the similarity of this signal, isn't it? in your statistics and the RSP, you learned about correlation of a signal. Okay,
Yes, sir.
can you hear?
Yes, sir.
The correlation or we have two types of correlation. One is called autocorrelation and another is okay. That extent they are similar. Are you getting noise or you the one of the intuitive and compare it, okay, isn't it? If you want to bring our signal back to our original time, what you need to do, you have to operate your signal in the time translation operation. Otherwise, it cannot bring back to your signal to the original time frame in order to compare them. Okay. So this shifting operation is very simple. Consider that we have a signal xt. This is illustrated here in this slide by using a consider that we have a signal something like this. It is a pulse centered at origin at equal to 0 with duration equal to 1 time unit. We are just making this shift that we want to prepare a signal yt. As an example, we said that how to verify this figure. Just by using the same example, that same technique that we have followed there. Okay, consider that we want to calculate the value of y0. Y0 would be equal to what?
X minus 2.
X minus 2. Is there any signal at x minus 2?
No, sir.
No, sir.
Then when your signal will begin to appear, for example, consider that we want to calculate y1. Your y1 would be equal to x minus 1. There is no any signal in x minus 1. Similarly, you calculate say y2. Y2 equal to what? Y2 would be equal
X of
to
0.
Y2 would be equal to
Sir, X of 0.
x0. Okay, so now this signal is going to y0, isn't it? In the same way, you will see that this edge is appearing at 3 divided by 2. This is appearing at 3 divided by 2. That is simply, we are adding, for example, our time minus half with what? With 2.
Yes, sir.
Isn't it?
Yes, sir.
Then every time will be shifted there. That generally, if we replace, for example, our 2 by t0, then actually this time will be equal to, this time would be equal to minus half plus t0, and this time would be equal to plus half plus t0. So this is what the shifting occurring to the right. Okay, if your t0 is positive, that just if your t0 is negative, your signal is going to the left. Okay, in this way you can shift your signal at your desired location. In many of our physical purposes, we need to shift this signal. Okay. Now, if we can combine these two equations together, because in many of our signal processing aspect, we need these two operations together. Okay. That means your signal can be operated, for example, in this way. In this way, your signal can be operated. That means we want to get a signal yt. That signal will be equal to xat minus b. So your scaling operation and time shifting operations are applied to this signal xt. Now, if these two types of signal is operating, then which operation should be made first? Okay, that means you need to assign the precedence of operation. Okay, that which operation should be made first. Okay, can you tell me, for example, from your intuition, that which operation should be taken first?
The shifting operation.
The shifting operation. Okay, this is written there, but still, can you verify it that shifting is needed first?
Yes, sir.
Why?
If we
Sir,
scale,
Because if we scale the signal, then what will happen? Your time will be reduced or expanded, but that
Yes, sir.
B is your original time scale. Okay, you can do that after your operation. Then you have to scale your B then. Okay, that means if you want to just make it independent of the precedence, then what you need to do? You have to express your signal in this way: X, A common, then it will be equal to T minus B by A, isn't it?
Yes, sir.
If
Yes,
it is
sir.
if it is B by A, then you see that your time is also, B is also a scale. B is actually time. So in order to understand this, you already got the trick. Then what you need to do, you have to shift your signal first, then you scale it. Or if you want to scale it fast, then you can shift it, but not B. You have to shift it by B divided by A. Okay?
Yes, sir.
So you just verify the rest of the thing by yourself.
Yes, sir.
Okay, and practice some problems. And if you have your question or other things, even you can arrange some tutorial class. Okay, if you want,
Yes, sir.
I can give you some further discussion on it. No problem.
Yes, sir.
Okay, all these examples are shown there. I have using simple pulses, another a bit complicated one. So try to just go through the slide, you will understand the thing very simply. Okay, this example or problem is taken from the second reference, Oppenheim's book, one of the best standard book written on signals and system. And
Yes, sir.
he is an MIT professor. This book is followed in MIT. Okay, now I am giving you a shortcut technique to sketch your signal. If you, just to perform these two operations, for example, simultaneously, okay, that you have to remember. That will help verify your answer, okay, that whether you are approaching in the correct way or not. Okay.
Yes, sir.
For example, say your shipment can be in positive direction, your shipment can be in the negative direction, or your scaling can be compression type, or your scaling can be expanded type, okay. But in all the cases, this technique will be applicable.
Yes,
even your signal can have different values, okay. We are dealing with a signal very simple, but your signal can be multi-valued signal, for example, within a time frame. In such cases, the same technique can be applied there by segmenting your signal in the same way. Okay, for example, consider that we have this signal, okay, not only a pulse, but we can have a signal something like this, we can have a signal something like this. Okay, that means you will see that you can split this signal into three different time regions, isn't it? And this technique that I am discussing from now ahead will be applicable for all these cases. Okay, then how to do that? Consider that we have a signal. Can you see this signal? The
Yes.
upper left one.
Yes, sir.
yes, sir.
So it is a pulse, simple, that you are required to find, for example, this signal. You are required to find this signal and sketch it. Okay. In conventional technique, what you need to do, you have to shift your signal to the left by 3 time unit. Then you have to compress it by 2, isn't it?
Yes, sir.
Yes, sir.
That conventionally you can easily do. Now, if you want to use this shortcut technique, that shortcut technique is simple. Okay, we have a lower bound of the signal, we have an upper bound of your signal. Okay, our new time frame is this 2t minus t. So in order to calculate the time of your new signal at the lower bound, you just equate this signal 2t plus 3 equal to minus 1, the lower bound of your original signal. Then you solve for t equal to minus 2. So this will be the lower bound of your shift of your resulting signal x2t minus 3. This is your lower bound. Similarly, you can equate it with upper bound, solve for t for your upper bound. This is your upper bound of your signal. So once these two time bound is you determine, then within this time bound is you compress your signal, the amplitude of your signal will be remaining same. In this way, you can also sketch your signal. Okay.
Yes, sir.
Yes, sir.
Sorry. So yeah, the multi-value signal is presented there. You have a portion from 0 to 1. You have a portion from 1 to 2. You have a portion from 2 to 3. Okay, you apply the, for example, 3 bounds separately. Okay, bound 1 is from 0 to 1. You find the lower and upper bound of this part. Similarly, you apply the thing for your bound 2. You apply the thing for your second, third bound. Then all this time will be calculated in the same way. Then you can sketch your signal easily. Okay, this is the decomposition of your signal into multiple signals. Okay, this is simply a puzzle type something. Okay, for example, say you have given a signal GT, and you have been asked to prepare the signal XT from GT. You understand the point?
Yes, sir.
You understand the objective of this thing?
Yes, sir.
That you have your
Yes, sir.
XT, okay? That XT, oh, sorry. Okay, you have your XT. That XT you need to prepare with the help of GT. A seed signal is given. Using that seed, you have to prepare this signal, okay? Now there exist many different ways to do that. What you can do, one of the ways can be something like this. You split your signal XT into many components, okay? You can see that you can, okay, if you can easily, this is a simple visualization technique. There is no any mathematics there, okay? So for this reason, I will not discuss much about it. It is a matching type technique, okay? You have to do it principally by your own.
Yes, sir.
Okay, this is your, for example, one component that lasts from 0 to 1. Then we have another component shifted, for example, one time unit, another component, something like this. If we add these all signals together, it will be this signal, okay?
Yes, sir.
You can easily verify it. Now, let us examine how G1T can be prepared from GT. Can you do that? Is it not the expanded version of your GT? G1 is the expanded version of GT.
Yes, sir.
Expanded and time shifted. That means what you need to do, you have to perform this operation GAT minus B to your GT, and you have to find the value of A and B. That will give you the equations that is needed to generate G1T. Here in this case, the upper bound of your signal -1 is given. The upper bound of your lower bound of your signal -1 is given, and lower bound of your G1 is also given. Upper bound of your G is given. Upper bound of your new signal is also given. Then unknown quantities will be A and B. Are not they?
Yes, sir.
Then your equation for the lower bound will be something like this. AT minus B would be equal to for your lower bound, your T would be equal to 0, and that is equal to -1. So you can easily calculate the value of B, isn't it?
Yes, sir.
In the same way, you can calculate the value of A. As a result, what will happen then? This equation, general equation GAT minus B can be derived for G1T, G2T, G3T, and G4T. Okay, just a very simple problem. I try to verify it. Solution is given in the next slide. Okay, verify that those things are correct. There might be wrong there. Okay, some incorrect thing can be there. You have to correct it. You have no reason to believe that your teacher is always correct. So all these things I have illustrated. So please have a look. Okay, inshallah you will understand it, I hope. So these operations are there with some examples that you can easily verify it. That this operation is actually independent of precedence that I have already discussed, because if we scale our time shipment with respect to the scaling factor of time, then either operation can be made first. The precedence rule already I have discussed, that this is summarized here. You please have a look. Now this operation is we want to do for a DT signal, okay? You see that for the DT signal, the operation will be what? In terms of integer values, not non-integer operation cannot be done, okay? So if we want to shift our signal, you have to shift either way, either to the left of your original signal or to the right of your original signal by an integer number of samples, okay? We cannot, for example, prepare a sample something like this, that you have, if your xn is given, we cannot say that make your xn minus half. Can we do that?
No, sir.
No, that means it can be n minus 1 or it can be n plus 1. So as a result, your shipment operation for your discrete time signal can be, say, we have our xn given, then your yn can be, for example, x say, n minus n0 or x plus n0, okay?
Yes.
So if it is x minus n0, it will be shifted to the right by n0 type number of samples, and it is plus, it will shifted to the right by n0 number of samples. In the case of scaling operations, the same that I have discussed, it will either downsample your signal or it will upsample your signal, okay? In this figure, you see that an illustrations is given, that original signal xn is given, your xn is shifted first by 2 time unit, then it is scaled by 3n. That's how it will look like. Okay, let us consider that we are scaling it by shifting it by 2 time sample points. Then you see that your sample point starts from this point. It is if it is 0, then this is n equal to minus 2, isn't it?
Yes, sir.
And this point is n equal to 2. It is actually a pulse, discrete time pulse centered at the origin. Now, if we want to shift it by 2 time samples to the right, then what will happen? Your n equal to minus 0 will go to where? N equal to 0. That means your result, if this is our signal, the general thing will be what? If you want to make this operation there, then this is equal to your minus 2 will be equal to minus 2 plus n0. Your plus 2 would be equal to plus 2 plus n0. Similarly, the intermediate values will be added with n0, isn't it?
Yes, sir.
So in our case, our n0 is equal to what?
Minus.
N0 equal to 2, isn't it?
Yes, sir.
So your minus 2 will go to 0 and your 2 will go to 4. So in this way, the intermediate values will be shifted. So this is what the shifted version of your original discrete time signal. Now you have to scale it. Scale means downsample, okay? So we are scaling it how many times? 3 times. What does it mean? It means that you are just picking every third sample of your shifted signal, isn't it?
Yes.
That means at any y0 would be equal to x3. So you have your x3 available there. So it is going at, at y0 would be equal to x0. So your y0, okay, intermediate signal is represented by v0 actually. So your v0 is this, v is this. So at y0, your value would be equal to v0, isn't it?
Yes, sir.
So v0 is this. So this is appearing at n equal to 1 in the last yn. Similarly, if we want to calculate yn, y1 would be equal to v3. So you have your v3, 1, 2, 3, you have your v3. This is appearing there. Now, if you want to calculate y2 equal to v6. Is there any v6?
No, sir.
So only we have these 2 samples you are extracting out. Okay, the other sample will be equal to 0. The same, okay? If you want to shift, you shift your signal first in the original time frame, then you perform the scaling operation on the shifted version, okay? If you want to just make the thing precedence independent, then what you need to do, you have to scale your sheep then with the same factor of your time scaling. Okay,
Yes.
my network appears to be a bit unstable.
Yes, sir.
Can you hear me?
Sometimes it is being distorted.
But no problem, but I have no hand on it, because if your network is not working, how can I do that? So this is the uncertainty, we have to bear it, okay? It is okay now? Now you can hear.
Yes, sir. Yes, sir.
Okay, then we have already, our operation is finished. Then we have to deal with few elementary signals that we usually encounter in our electrical engineering. Okay, I will not be discussing about those things. This is has been discussed from your first year. Okay, this is your exponential signal, and you know how exponential signals changing with time, and you have to understand it. Now our DT signal of this type can be something like this. Okay, consider that we have a signal xn is equal to b into r to the power n. Now you see that if your r can be less than 1 or your r can be greater than 1. So if your r is greater than 1 and if your n is increasing, then what will happen? This signal become an unbounded type signal, isn't it?
Yes, sir.
Because if your r is greater than 1, if your r is greater than 1 and you and your r is greater than 1 and n is increasing from 0 to infinity, say, then what will happen? Your signal value will be gradually increasing and it will become unbounded.
Yes.
So for in reality, your b should be unbounded and r should be less than 1, then it will get a bounded signal. Okay. So three scenarios are expressed there. You will understand this scenario. You can plot this thing by using your computer or even hand to understand how a discrete time exponential type signal works. And this point, from this point, it is very important. You have to be concentrated about this, okay? Consider that we have a sinusoidal signal. We have our sinusoidal signal we are encountering from very beginning, okay? It will have some notational differences is there in this slide. Forget about this. You have to use the same notation that is there in your textbook, okay? Our continuous frequency will be, it is reverse here. Okay, continuous frequency will be equal to, because
Sir, are you there, sir?
Sir may be disconnected.
hello, can you hear me?
Yes, sir. We can hear you now, sir.
Yes, sir.
Is it okay?
Yes, sir.
Yes, sir.
Because network was disconnected. So this is your continuous time sinusoidal signal, okay? Please respond, otherwise I will not understand that
Yes, sir.
I am
Yes,
with
sir.
you or not. So this is your continuous time signal with frequency equal to omega. It has an amplitude, it has angular frequency, phase, you know this thing. And similarly, time period can also be calculated from your frequency. Similar expression for a discrete time signal is this, but it needs further discussion that not always, okay, for any value of omega, your signal can be in continuous time, your signal can is periodic. But this is not true for your discrete time signal. What is the difference that we need to carefully understand, okay? Otherwise, because it belongs to our sampling and all other issues, we will be discussing this thing, okay? Just consider this signal, okay? Okay, let me explore it, then I will go to. Okay, I am skipping few slides, then I will again be going back there. Okay. Can you see this slide?
Yes, sir.
Yes, sir.
এই রেসপন্ড সাথে সাথে না করলে আমি ক্লাস
Yes, sir. Yes, sir.
নিতে পারবো না, আমি তো বুঝতে পারতেছি না।
Sir, your voice is being distorted.
Sir, your network is
We are
unstable, I
responding,
think.
sir, but I think you have some network problem.
That network problem I have, but at this moment I have no any alternative, okay?
Yes, sir.
This is very difficult to continuously 75 minutes lecture.
Yes, sir.
So consider, okay, we are not considering our cosinusoidal and sinusoidal generally. We are considering an exponential signal in general, okay? That exponential complex signal will contain both your cosine omega 0 t plus j into sine
Omega 0 t.
omega 0 t. So this analogy will be very general, okay? If we want to sample this signal, for example, say that we have to take, for example, n samples of your signal in ts time, for example. So we have to sample in an interval, sampling interval ts. Then we have to replace our t by nts. So your discrete time signal will be this, okay? E to the power omega 0 nts, or omega 0 say is the frequency, fundamental frequency of your angular frequency. Now we have to find the condition that what ts will make your xn periodic, okay? Not all sampling time can make your signal periodic. If you want to understand this, because you know that this signal is a discrete one, if it is periodic, it will be periodic for say after n0 numbers of samples. Consider that. That means if this signal is xn, that xn would be equal to xn plus n0. Okay, that means the period of use, fundamental period of use signal will be n0. After n0 numbers of sample, it will be repeated. So if this is the case, then okay, consider this equation. Here it is e to the power j omega 0 t, n is replaced by, this signal is nothing but x n0 n plus n0, replacing n by n plus n0. Then if this signal is to be n0, x0, then what will happen? This quantity e to the power j omega n0 ts must be equal to 1. And you know that this can be equal to 1 if it becomes an even multiple or integer multiple of twice pi. We know that e to the power m twice j m twice pi equal to 1. Then this will
We
give
not
you,
understand this part, sir. Why it must be 1?
sorry,
So why it must be 1?
can you see this equation? Why it should be 1? Because if your signal should be periodic, then xn plus n0 must be equal to xn. This is your xn. This is your xn plus 1, 0. Then in the intermediate step is simple. You are splitting this factor into two multipliers.
Yes, sir. Now I get it, sir.
So if this is not the case, then this quantity should be equal to 1. If this is 1, then that exponent this exponent should be equal to integer multiple of twice pi. Then if this is the case, we can easily derive this condition that will make you sample version of your exponential sinusoid what we call a periodic one. That means the ratio of your sampling time and the time period of your signal must be a rational number. Do you know what is rational number? Rational number means it must be equal to integer of ratio of
Two integer value.
two integer values that we have discussed in the last class. Okay. Either this can be there or it can be made an integer by using some technique that we have discussed earlier. Okay. So in this way, what you need to do, we can easily find the conditions. Okay. Now, if this condition is the condition, okay, then for your sinusoidal signal, what you need to do, you have to okay, you try to understand this scenario by yourself by using this technique. Okay, but I am again going back, for example, to the slide that I skipped. Okay, consider this thing. Or let me use okay, without using this thing, let me use whiteboard. Okay, it is there explained in your book. You'll understand it, I hope, because this needs some further explanation. Okay. Consider that we have a signal, say that I have already told you that we have a signal, say e to the power, say j, consider that your omega 0 n. This is your xn. If this is our xn, then if it is to be periodic, for example, for how many numbers of samples, say x into n plus n0 numbers of samples. Then this is, you can replace your e to the power j omega by n plus, say n plus n0.
Yes, sir.
Okay. And that will be equal to e to the power j omega n into e to the power j omega n0, isn't it?
Yes, sir.
Then if they are to be equal, then e to the power j omega n capital N0 must be equal to 1.
Yes, sir.
And that can be equal to m into twice pi. That means your j omega n0 would be equal to m into twice pi, isn't it? J m into twice pi, where m is an integer.
Yes, sir.
Sir.
Then you can easily find that your n0 would be equal to what, then m into twice pi divided by capital N0, isn't it?
Sir.
Is it okay? No. Omega. Is it okay?
Yes, sir.
Yes, sir.
So then what will be happening? Is there any, because your n should be integer. If your n is integer, then that ratio should also be an integer, isn't it? Would not be this
Yes, sir.
ratio integer?
Yes, sir.
This is what the thing condition. Okay, for exponential signal, if your frequency is given, no, in not always that frequency, that omega will make you signal periodic. Okay, if this condition is not satisfied, then it will not be periodic. And you have to apply, for example, we can make, okay, if we have a rational number, that rational number, for example, can be what we call make integer by using a multiplier m. Okay, that I have discussed in the last class, that if we have a two number rational number expressed in this way, we can make it an integer by multiplying it with a factor equal to m. That can make you signal that will make you rational number an integer. Okay, so with this thing, let me take your percentage. Okay, we will be moving this point ahead. You remember the slide number that we discussed today. Okay, you can stop your recording now.